Hi, in this video today we're going to think about how we might take powers of complex numbers, and what we're going to do is start off by thinking about them in complex exponential form. So we're going to be using a theorem called de Moivre's theorem that states that for any integer n, z to the n, where z is a complex number, equals r to the n e to the I n theta. So that's a nice compact way of taking powers of a complex number. So first up, let me just try and give you some kind of idea of why this might be true. So if we have just our regular complex number z equals r e to the I theta, and I multiply it by z, so I've got z squared. Then this is just equal to r e to the I theta times r e to the I theta, where r is the modulus of z and theta is the argument of z. And we have a result from earlier in our work that said if you multiply two complex numbers together, what you do is you multiply their moduli, so that's r squared, and you add the angles. So this is just equal to r squared e to the I 2 theta. So that's just the product of two complex numbers. Okay, so if that's z squared, let's multiply that by z again, and that means we've got z cubed. So that's just r squared e to the I 2 theta times r e to the I theta. So again, we multiply the moduli together and add the angles. Okay, so you can see how we could keep doing that, and we could keep multiplying over and over and over again by z, and this formula would build up. To do this for all possible values of n, we can use a technique called proof by induction. And we're not going to do that in this course, but this is the sort of thing that would lend itself to such a proof, and you can do that in real analysis next year if you come back and do some more maths with us. Okay, but note for now, you can sort of see how this might go the more times you multiply z by itself. You might also note that this fits in with our usual laws for the exponential function. So if you had just the exponential function that was the real exponential function from r to r, then the rules for the exponential function say if you have e to the x squared, then that's the same as e to the 2x, for example. So here we've got this function raised to the power n, so that's just r to the n times e to the I theta to the power n, and so we just multiply the exponents together. So that's what we would expect when we're thinking about the real exponential function. This result is really handy if you're trying to work out something like this, 1 plus I root 3 to the power 8. If you tried to do that by multiplying out the brackets, it would take you rather a long time. But if you use de Moivre's theorem, it's actually quite fast. So I'm going to use de Moivre's theorem. If you don't believe me, you can start multiplying that out 8 times, and we'll see who finishes first. So the first thing I have to do is write z as in complex polar form. And so I have to write this as r e to the I theta, where r is equal to the modulus of z and theta is equal to the argument of z. Now this is an example of complex number that we've seen a lot of times before, so you shouldn't have too much trouble writing this in exponential polar form. So the modulus of z, of course, is just the square root of the real part and the imaginary part. So that's equal to the square root of 4, so that's equal to 2. And the argument of z equals theta, where tan theta equals y on x. So in our case, that means that tan theta is equal to root 3 on 1. And by now we know that theta is equal to pi on 3 because 1 plus root 3i is in the first quadrant. So we just need to go around pi on 3. So we've got z equals 2e to the I pi on 3. And so by de Moivre's theorem, z to the 8 equals 2 to the 8 e to the I pi on 3 times 8. So that equals 2 to the 8 e to the I 8 pi on 3. 2 to the 8 is 256. And we just have to be a little bit careful here because you can see that 8 pi on 3 is not an angle in minus pi to pi. So we have to write this as an angle in minus pi to pi. So if we go around the circle completely, we go around 6 pi on 3. So this is actually equal to 2 pi plus 2 pi on 3. So the angle we're looking for is just the 2 pi on 3. So this is e to the I 2 pi on 3. So now we just want to write that back in Cartesian form. So we write z equals 256 cos of 2 pi on 3 plus I sine 2 pi on 3 and cos of 2 pi on 3 is just minus a half. Sine of 2 pi on 3 is root 3 on 2. So this is 128 times minus 1 plus I root 3. So really it's not too much harder than just finding the complex exponential form of the complex number to start with. So the next thing we have is an example for you to try yourself. So write your complex number in complex exponential form and then use de Moivre's theorem to raise that to the power 14. Okay. Okay, so now we're going to use the complex exponential to derive some trigonometric identities. And the first thing we're going to do is just recall the binomial expansion of an expression that looks like this. Some of you may be familiar with Pascal's triangle, others might not have seen it before, so it's worth spending a little bit of time looking at Pascal's triangle. So in your notes there's a mistake. There should be a 1 right up the top of this triangle. Somehow the 1's ended up over here, so in your notes we'll use that on the side to just explain what's going on in Pascal's triangle. If you've seen this before, then you might want to skip ahead a little bit in the video. Okay, so in Pascal's triangle, how do you construct it? Well, you start off with a triangle like that that has 3 1s. And then the next thing you do is you add up these two numbers and you get 2, and then you add a 1 at either end. In the next row, you add up these two numbers, you get 3. You add up the next two numbers and you get 3, and then you add a 1 at either end. And you continue doing that, so that's a 4, that's 6, that's 4, and we end up with a 1 at either end. And you can continue like that for as long as you like. And it turns out that in each row you get the coefficients of the expansion of an expression that looks like that for an appropriate n. So let's use that to just do a general expansion. So we're going to start off just with an example of expanding this simple expression, a plus b to the power 5. And you'll know when you start expanding this, you start off with powers of a that start at 5 and decrease to 0, and powers of b that start at 0 and increase to 5. The coefficients of the terms come from Pascal's triangle. Okay, so let's try and put this together. So we're starting off with powers of a that start at 5. So what do I mean by that? Well, we're going to have a term that's got an a to the 5 and it's going to have a b to the 0 multiplier. The next term is going to be a to the 4th times b to the 1. Then we're going to have a cubed times b squared. Then a squared times b cubed, a times b to the 4th, and then a to the 0 times b to the 5. So b to the 0 is just 1, of course, so this is a to the 5 plus a to the 4th b plus a cubed b squared plus a squared b cubed plus a b to the 4th plus b to the 5th. Now it's not quite finished yet because not all the coefficients are going to be equal to 1, but here's where we go back to Pascal's triangle. So let's just go back up to the previous page. And you'll see that we need to use this row of coefficients. The coefficients are going to be 1, 5, 10, 10, 5 and 1. So we just say 1, 5, 10, 10, 5 and 1. Let me write that a bit clearer here there so you can see it. Okay, so that's the expansion and how you use Pascal's triangle. So you can see that the powers of A are decreasing, the powers of B are increasing, and the coefficients are from Pascal's triangle.